Today we're diving into the fascinating world of colloidal systems, focusing on gels and emulsions. These materials are all around us, from the food we eat to the products we use daily. Understanding their structure, properties, and uses helps us appreciate their importance in science and industry. In this video, we'll explore what gels and emulsions are, how they're formed, their different types, and where you encounter them in everyday life. Let's start by breaking down the basics of colloidal systems and why they matter. Colloidal system consists of two main components, the dispersed phase and the dispersion medium. The dispersed phase is the substance distributed throughout the system, while the dispersion medium is the substance in which the dispersed phase is spread. For gels, the dispersed phase is typically a liquid and the dispersion medium is a solid. For emulsions, both the dispersed phase and the dispersion medium are liquids. This distinction is crucial for understanding the behavior and properties of gels and emulsions. Gels are unique colloidal systems where a liquid is dispersed within a solid medium. The process of forming a gel is called gelation. Imagine fruit jelly or agar-agar. These are classic examples of gels. In these, the liquid forms the discontinuous or dispersed phase while the solid acts as the continuous or dispersion medium. Gels are semi-solid and elastic, making them distinct from other colloidal systems. Their structure allows them to hold shape while still containing a significant amount of liquid. Formation of a gel or gelation occurs when a sol, essentially a colloidal solution, coagulates under suitable conditions. During this process, the liquid becomes the dispersed phase and the solid forms a continuous network, trapping the liquid inside. This network gives gels their characteristic texture and elasticity. Common examples include jellies, jams, and curd. The transformation from sol to gel is a fascinating process that underpins many foods and materials we use. Structure of a gel is quite intricate. It consists of a solid network that holds the liquid in place, creating a semi-solid mass. This network is responsible for the gel's elasticity and ability to maintain shape. The solid phase forms a continuous matrix while the liquid is distributed throughout. This structure is visible under a microscope and is key to the unique properties of gels, such as their ability to swell or shrink depending on environmental conditions. Gels can be classified based on their mechanical properties into two main types, elastic gels and non-elastic gels. This classification helps us understand how different gels behave under various conditions. Elastic gels are flexible and can regain their shape after deformation, while non-elastic gels are rigid and do not recover their original form once altered. Let's take a closer look at each type and see how they differ in structure and application. Elastic gels are those that shrink by losing liquid when evaporated but retain their elastic property. They can be reformed by adding liquid, making them reversible. These gels possess elasticity, meaning they change shape when a force is applied and return to their original shape when the force is removed. Examples include gelatin, starch, and soaps. Elastic gels are typically formed by cooling concentrated lyophilic sols, and their structure is held together by electrical attractions rather than rigid bonds. Some common examples of elastic gels include fruit jams, gelatin desserts, and agar-agar. These substances are widely used in the food industry for their texture and ability to hold shape. When you press on a jelly dessert, it wobbles but returns to its original form. This is elasticity in action. The molecular structure of these gels allows them to be flexible and resilient, making them ideal for culinary and industrial uses. Unelastic gels, on the other hand, lose their elastic property when they shrink and cannot regain their original form by adding liquid. These gels are irreversible and rigid, often formed by chemical reactions. Silica gel is a prime example, produced by adding hydrochloric acid to sodium silicate solution. The resulting network is linked by strong covalent bonds, giving the gel its rigidity. Non-elastic gels are used in various industrial and laboratory applications. Unelastic gels like silica gel are prepared through specific chemical processes. For instance, when concentrated hydrochloric acid is added to sodium silicate solution, silicic acid molecules polymerize to form a rigid silica gel. This gel has a strong covalently bonded network, making it ideal for use as a desiccant or adsorbent in laboratories and industries. The preparation method determines the gel's final properties and application. Gels exhibit several unique properties that set them apart from other colloidal systems. These include imbibition, syneresis, and thixotropy. Each property affects how gels interact with their environment and determines their suitability for different uses. Let's explore these properties in detail to understand how they influence the behavior of gels in practical applications. Imbibition is the process by which gels absorb water or other liquids, causing them to swell. This property is particularly evident in elastic gels, which can take in significant amounts of liquid and expand in size. Non-elastic gels, however, do not show imbibition. This ability to absorb and retain water makes gels useful in various applications, from food products to medical dressing. Syneresis refers to the shrinking of gels as they lose water when exposed to the atmosphere. This process, also known as weeping, is common in gels that are left out for extended periods. As the gel loses water, it contracts and may even release liquid onto its surface. Understanding syneresis is important for maintaining the quality and texture of gel-based products. Thixotropy is a fascinating property where some gels become liquid sols when shaken and revert to their gel form when left to stand. This reversible transformation is seen in certain gels like iron oxide and silver oxide. Thixotropic gels are semi-solid at rest but flow like a liquid when agitated. This property is valuable in products that need to be easily applied but stable when stored. Gels are everywhere in our daily lives. From food items like starch, jams, and jellies to household products like soaps and boot polish, gels play a crucial role. In the laboratory, silica gel is widely used as an adsorbent and desiccant. Solid alcohol gel made by mixing calcium acetate with ethanol serves as an emergency fuel. The versatility of gels makes them indispensable in both domestic and industrial settings. Let's compare elastic and non-elastic gels. Elastic gels are formed from high molecular weight organic substances like starch and gelatin, and they give an elastic solid upon dehydration. They are reversible and show imbibition. Non-elastic gels, on the other hand, are made from low molecular weight inorganic substances like silica gel. They give a solid powder on dehydration, are irreversible, and do not show imbibition. This distinction is important for selecting the right type of gel for specific applications. Now let's shift our focus to emulsions. Emulsions are colloidal systems where both the dispersed phase and the dispersion medium are liquids. These systems are common in everyday life from milk to lotions. Emulsions are mixtures of two or more immiscible liquids, meaning they don't naturally blend together. Understanding emulsions helps explain the science behind many foods, medicines, and industrial products. Emulsion is a mixture where tiny droplets of one liquid are dispersed throughout another liquid. The two main components are the dispersed phase and the dispersion medium, both of which are liquids. Classic examples include milk, where fat droplets are dispersed in water, and cod liver oil. Emulsions are stabilized by substances called emulsifiers, which help keep the liquids from separating. To better understand emulsions, imagine a glass of milk or a bottle of salad dressing. If left undisturbed, the liquids may separate into layers. However, when shaken or mixed with an emulsifier, the droplets remain suspended, forming a stable emulsion. This visual difference is key to identifying emulsions in everyday products. Emulsions are classified based on which liquid is the dispersed phase and which is the dispersion medium. The two main types are oil in water (OW) and water in oil (WO) emulsions. In OW emulsions, oil droplets are dispersed in water, while in WO emulsions, water droplets are dispersed in oil. Each type has distinct properties and uses, especially in food and skincare products. Oil in water (OW) emulsions have small oil droplets dispersed in a larger amount of water. Milk is a classic example where fat globules are suspended in water. These emulsions are lightweight, easy to spread, and quickly absorbed, making them ideal for products like vanishing creams and lotions. OW emulsions are also common in food and cleaning products. Water in oil (WO) emulsions consist of water droplets dispersed in oil. Cod liver oil and cold creams are typical examples. These emulsions are thicker and provide a protective barrier, making them suitable for skincare products that prevent moisture loss. WO emulsions are also used in certain industrial and pharmaceutical applications. Emulsions share several properties with sols, such as Brownian motion and the Tyndall effect. They can also undergo demulsification, where the two liquids separate into distinct layers. This can be triggered by heating, freezing, centrifugation, or adding electrolytes. Understanding these properties is essential for maintaining the stability and effectiveness of emulsions in various products. Emulsification is the process by which an emulsion breaks down into its separate liquid components. This can happen naturally over time or be induced by physical or chemical means. For example, heating or adding certain chemicals can cause the emulsion to separate, forming two distinct layers. This property is important in both industrial processes and product formulation. Emulsions are incredibly useful in daily life. For instance, phenol forms an oil and water emulsion used as a disinfectant. The cleansing action of soaps and detergents relies on the formation of emulsions to remove oil stains from fabrics. Emulsions are also used in medicines such as cod liver oil and in industrial applications like road construction, where asphalt is emulsified in water. In industry, emulsions play a significant role. They are used in the manufacture of oil paints, where pigments are dispersed in oil and water. Asphalt emulsions are crucial for road construction, providing a stable mixture that can be easily applied and set. The ability to control the properties of emulsions makes them valuable in a wide range of industrial processes. Let's compare gels and emulsions side by side. In gels, the dispersed phase is a liquid and the dispersion medium is a solid, resulting in a semi-solid elastic mass. In emulsions, both phases are liquids, making them mobile and fluid. Gels can swell or shrink, while emulsions cannot. Each system has its own types and examples, such as gelatin for gels and milk for emulsions. Summarize: gels and emulsions differ in their composition, structure, and properties. Gels are semi-solid, elastic, and can absorb or lose water, while emulsions are liquid mixtures that remain mobile. The choice between a gel or an emulsion depends on the desired application, whether it's food, medicine, or industry. Recognizing these differences helps in selecting the right material for the job. Here's a quick visual recap. Gels are semi-solid masses with a liquid dispersed in a solid, like jelly or silica gel. Emulsions are mixtures of two liquids, like milk or cod liver oil. Both systems are vital in everyday life and industry, each with unique properties and uses. Understanding their structure and behavior is key to harnessing their full potential. Conclusion: both gels and emulsions are essential colloidal systems with wide-ranging applications. From the food we eat to the products we use in the industries that drive our economy, these materials are everywhere. By understanding their properties and differences, we can better appreciate their roles and make informed choices in science, technology, and daily living. Thanks for joining this exploration of gels and emulsions.